Hello everyone. In this video, we will try to review the stack and queue data structures. Let me open a couple of slides and then let's start with it. Okay. So in the previous video, we revisited the array and linked list data structure. And upon those arrays and linked lists, in this video, we will polish our knowledge about the stack and queue. Actually, stack and queue data structures are all built by using the array and linked lists. Okay, so let's start with the stack. So for the classical definition of the stack data structure, actually we start with the plate example. So let's assume in the kitchen you are washing the plates. Okay. So you wash the first plate and put it aside. And then you wash the second plate and you place it on top of the previous one. When you wash the third one, so you will put it on the top of the second one. So that means the plate that you wash last will appear always at the top of this stack. And whenever you would like to pick a plate from that stack, you will be getting the one that is on the top of the stack, and you know that that is the last plate placed into that stack. That is why stack data structure is called last in, first out. Okay. So surely you can also say that this is a first in, last out data structure, but this one is more widely used. With the abstract definition, whenever you have a data structure, you have an abstraction. So let's remember what abstraction was. Abstraction provides us the main functionality and properties of data structures. They do not tell us anything about the implementation, but they tell us about the functionality. With the abstract data type, with the stack, so you have to have those operations. The first one is the push operation. I would like to insert something into the stack. So that is the push operation. Whenever you would like to get something out of this stack, you would like to pick something from this stack. So that is the pop operation. Sometimes we might need to check what is appearing at the top of this stack without popping it up. Then I have the top operation. With the top, you are not making a pop operation. You are only observing, checking what is at the top of the stack. Similarly, you might be curious about whether the stack is empty or not. And there should be other functions checking the number of items in the stack or the stack size. For instance, if you are implementing a stack with an array, you just initiate the array with a size. So let's say the length. So the length of this array is, let's say, 10. That means you can place 10 elements into this array. And if this is a stack, its capacity is 10. But there might be less than 10 elements at any time in the stack. So you can just refer to this one with the size and maybe the length referring to the capacity. Okay. Here is a small sketch of stack operations. Particularly the most important ones are the pop and push operations, So these are the push operations. So let's assume the stack is initially having only integer 1 in it. So when you push 2, 2 will appear at the top of 1. And then when you push 3, 3 will place at the top of 2. Okay. And then 4 and then 5. Okay, so this is the first one inserted, and this is the last one inserted. That is why when you pick one item from this stack, meaning that you are applying the pop operation, you get the top item. So at the top, you have the 6 here. And then if you continue applying the pop operations, 6, 5, 4, 3, 2, so those will be the ones. For the implementation, mostly stacks are implemented with an array. So this is a simple array starting, so zero-based indexing, let me use. Okay, so I have an array of size n. Whenever I would like to push something into this array, I will write it to the last available position. So let's write 5 here, and then let me push 2, let me push 4, let me push 6, whatever. But I should know the last position that I have written. Okay, so in this case, the last item that I have written is at position 3. Okay, so this is, you may think of this as a pointer. Okay, and when you would like to have the pop operation, what happens is you go and take this out and move your pointer to the left by 1 position. Whenever you would like to push one thing into this stack, you first move your pointer to the right by 1, and then push whatever you would like to insert into this array. So that is the basic functionality in the stack data structure. Okay. I think it will be better to have a working example for better understanding of the stack. So again, this is a classical example of parentheses verification. So I'm given an expression, and in this expression, there are some number of different types of parentheses. What I would like to check is there should be equal number of opening parentheses with the closing parentheses, and more of that number, so they should match in their order. Okay, so whenever you have an open parentheses, so there should be a closing parentheses just next to it, right? And their types should match. So let's try to answer this question with a stack data structure. What I will do is I will read the expression from left to right. Whenever I see an open parentheses, I will push it into the stack. And whenever I see a closed parentheses, I will go up the top item from the stack, compare it with the close parentheses. If their types match, then I continue. If there is a mismatch, that means there is a problem with the parentheses in the expression, and you report an error. Okay, so what if you encounter something other than the open or close parentheses? You simply skip that. So, okay, so let's make it quick. So I start with this one. Okay, so I push it into the stack. So that's a curly bracket. And then I have an open parentheses. I have another open parentheses. I have 5, skip it, plus sign, skip it, 2, skip it. And then I have a close parentheses here. Okay, a close parentheses. Whenever I see a close parentheses, what I will do, I will go to my stack, up the top item, compare these two guys. In this case, they are matching, so that is fine. Now I'm left with the stack, the open parentheses at the top and a curly brace at the bottom. So what I expect on the next closing parentheses, we will see what will happen. Okay, so we continue. So that is the multiplication sign. So you just skip it, and then you have this square bracket. So that's an open square bracket. So you push it into the stack, and then open parentheses, you push it into the stack, skip it, skip it, skip it, and then there is a close parentheses. Since that's a close parentheses, I will go to the stack, take the top one, compare them, they match. Okay, I continue. So that's popped up and I'm left with the square bracket on the top of the stack. And we continue and we see that, oh, okay, I see another closing parentheses. Now this is the closing parentheses. I go to the stack and take the top item. It is this one. But unfortunately, this time they do not match. And you say that there is a problem with the parentheses correctness in this expression, and you report a failure. To understand why stack is very useful in this scenario, I strongly suggest you to think about solving this problem without using a stack. Okay, and then you will see that it will be a lot more messy and inefficient. However, I have another example, I think more elegant to share with you. Okay, so now this time our problem is there is a party, and in this party there are n people, and one of those guys is a celebrity. Okay, a celebrity, a very famous person, which means that famous person does not know anyone in the party, but all the others know that celebrity very well. So this is the definition of the celebrity. Okay, so this is the definition of the celebrity, who is known by everyone, and the celebrity does not know anyone in this party. Okay. The question is, how can you find the celebrity in a given party of n people? The straightforward solution would be, I will pick one person from that party, and I will check all the remaining n minus one guys to see whether this is a celebrity or not. If this is not a celebrity, I will pick the next guy. I do the same check with that. So with just two for loops, right? However, there is a better, more elegant way of achieving this task. So let's assume I denote the people in the party with this notation, A1, A2, AN. And here is the crucial observation that helps me to use the stack data structure, how it works. So in a pair of two people, so let's say AI and AJ, you ask this question, does AI know AJ? If the answer to this question is yes, then you can immediately decide that AI cannot be the celebrity. Why? Because you asked, does AI know AJ? And it says, yes, AI knows AJ. By definition, celebrity does not know anyone. Since AI knows AJ, AI cannot be the celebrity. If the answer to this question is no, similarly, you can immediately understand that AJ cannot be the celebrity, because by definition, a celebrity is a person who is known by everyone. If AI doesn't know AJ, then AJ cannot be the celebrity. Okay. And then here is the elegant part. So let's assume I'm using a stack, and I put all the people in this party in the stack. Okay, so A1, A2, whatever, AN minus 1, AN. By the way, it should not be following this order, so any random order will work. What you will do is, once everyone is in the stack, so you will perform a pop operation, and a second pop operation. So this will bring you in our example, so an and an minus 1. And you ask this question, does an know an minus 1? And according to the answer, either an or an minus 1 cannot be the celebrity. Whoever cannot be the celebrity, you eliminate it. So let's assume an minus 1 cannot be the celebrity. By the way, since you have taken these out, okay, so an and an minus 1, so they are already popped out, and we have an minus 2 at the top of this stack. Who is alive here? An. So you pop the next element, which is an minus 2, and you do the same thing with it. Okay, so you pop this out. Okay. And again, according to the answer, one of these guys will be eliminated. So let's assume it's an now, and you got the idea, right? So during the traversal of this stack, actually I will be performing n pop operations, and at the end there will be only one person surviving here, and this one is the celebrity. The difference between doing this with the straightforward brute force method and the stack data structure, it is because with the stack data structure, you can do it in linear number of operations. However, if you are using the brute force method, then you will need quadratic number of operations. But we will go and do this analysis later in the upcoming videos when we study the asymptotic notation and the big O complexity later. Okay, good. That was for stack data structure, and now similar to stack data structure, we have the queue data structure. With the queue, it is first in, first out. Whenever you go to a bank, you get a number from the queuematic, right? So whoever arrives to the bank first should get the service first. So that is called first in, first out. Another classical example is you are waiting on the bus stop to ride on a bus. Whoever arrives to the bus station first should ride on the bus first, right? So that is why we call this the first in, first out data structure. Again, you can make it last in, last out as well. So for the queue abstract data type, we have the following operations. So the in queue means you would like to insert something into this queue. Insertions will always happen at the back of the queue. So in queue just inserts an item to the end of this queue. And dequeue operation means you are fetching someone from this queue, and dequeue always happens from the front. So like the push and pop operations with the stack, we have the corresponding in-queue and dequeue operations in the queue. Similarly, you might be curious about who is at the back, who is at the front, the length and the size, capacity, and the number of items in the queue. So those are the other functions, properties you should support in your implementation. Again, for the queue, you can use an array or a linked list. If you are using an array, again, you will be inserting the items to the end, but whenever you would like to get someone, you will get the first item. That means you will need 2 pointers, right? So this is the first item and this is the last item. Whenever you fetch someone, you cannot put anyone here again because you will just forward the operate front pointer to the next position, and you will not be using this one. I guess you already realized that after a couple of dequeue operations, what will happen is if this is your initial array, so it is first compartments will be empty and they are unusable. So actually this space is being wasted, right? So if you don't want to waste space, you may prefer to using a linked list based implementation of a queue. Why? Because with the linked list, as you remember, it is easier to perform insertion and deletions. Whenever you make a dequeue operation, you simply delete this one and give it back to the memory. Okay, so this way you will not be losing space. Okay. So here is a quick example to see the first half of a given sequence with the second half by using a queue and a stack. So this is an example sequence given 1, 2, 3, 4, 5, 6, 7, and 8. So this is the first and this is the second half. Interleave means you will get an element from the first half and then from the second half. So 1 and 5. And then the next element. So at the end, it will turn into 1, 5, 2, 6, 3, 7, 4, and 8. Okay, and I'll be using one queue and one stack. With the vertical representation, I will be referring to the stack. With the horizontal, I will be referring to the queue. So this is my queue and this is my stack. Okay. So I start with the first step. I will push the first half into a stack. Push 1, push 2, push 3, push 4. And the remaining guys, the remaining items, they are staying in the queue. And in the second step, we in-queue from the stack. So what it means, I will go and pop the first item from the stack, which is 4, and I will in-queue it to the stack, in-queue it to the queue. This is done. And then the next one is 3, so it comes here. The next one is 2, it comes here. And the next one is 1, it comes here. With these first two operations, what you did is you just moved the second half to the position of the first half, and then reversed the second half and attached it to the first one. Okay. On the third, so let me just clear what I did before. So now for the third one, I have this one ready from step 2, and I will dequeue and inqueue the first half. So 5 dequeue and then inqueue, which means you will move 5 to here. And then 6, it will come here. And then 7, it will come here. And then 8, it will come here, and you will stop. At the end of the third step, compared to the initial input, what happened is you just reverse the first half, right? And then the second half, it is as is. You continue with the fourth step, push the first half into the stack. Now I'm pouring this back into the stack. Push 4, push 3, push 2, push 1. That is why 4 is at the bottom. And then beginning with the fifth one, what we start the interleaving. Interleave the elements from the stack and the queue. Okay, so what is at the top of the stack? It is 1. Okay, so what you do is you get this 1 and in Okay. And then the next one, what is get this out? This is not very intuitive, but this is a good example to study the basic mechanisms in stack and queue data structures. Okay. What I can suggest you as more intuitive and interesting and a bit more challenging examples to study to understand the stack and queue are those ones. Okay. So the first question I can suggest is, how can you implement a queue by using two stacks? Which means I will be using two stacks. I can have only push and pop operations here. However, at the end, I will have a mechanism to implement enqueue and dequeue operations. How can you implement enqueue and dequeue by using two stacks? Okay, so this is the first thing you may study. And the second one is usually whenever we have an array of numbers, integers, real numbers, whatever, we are curious about the next greater, next smaller, or the previous greater, previous smaller elements. For instance, let's assume in this array here, I have 100, and I have, let's say, 5 here, 50 here, and let's say 200 here. So what is the position of the next greater for 100? So it is 200, right? And for the next smaller, again for 100, so it is just the next item. You can also think of it for the previous items. So this is called the next greater, smaller, previous greater problems. And a more real life implication of those problems is the stack span problem. You may find the definitions and the solutions from the internet and study those questions. Particularly the second one will give you a better understanding of using stack. And the first one will give you a better understanding of queue and stack together. Okay. Anyways, so that is all I would like to share with you about the stack and queue data structures. On the next video, I will try to cover the tree and graph data structures. By the way, these videos are just reviews, okay? So we assume that you already know those data structures, but since we'll be studying the algorithms, we will need to refer to those data structures very frequently, just polishing our knowledge and maybe adding a little bit new perspective. Okay, thank you so much and see you soon.